Hello students, welcome to another video of F.Y.B.Sc calculus. Today we will start the second chapter. Second chapter is sequences. So in this chapter we will see the definition of sequence and convergent sequences. So first of all we will start the chapter by definition of sequence. Definition of sequence. In day-to-day life we use this word sequence. If we arrange some things or some objects in definite manner, then we say that arrangement is sequence, or these objects are arranged sequentially. Objects are arranged sequentially. Now, in the mathematics, the definition of sequence is some different. The sequence in mathematics is a function from set of natural numbers to real numbers. So, first of all, the definition of sequence and this sequence in real numbers. A sequence of real numbers is a function defined on the set of natural numbers set n of natural numbers whose range is function defined from set of natural numbers to the real numbers whose range is contained in the set R of real numbers. So in another word we can say that sequence means it is a definite rule which gives the arrangement of natural numbers in real numbers. For example, if we write suppose first of all we will take the notation of that sequence xn. The notation is denoted by sequence xn. N is from 1 to infinity. Here n is the set of natural numbers. For example, if we take this set, suppose 1, 2, 3, 4, 5, this set 1, 2, 3, 4 means this set S is itself the set of natural numbers. These numbers 1, 2, 3, 4 are arranged in definite manner, because after 1 there is 2. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So this set we can say that this is the sequence of this sequence xn, n running from 1 to infinity. And if we denote or if we arrange this by some function, suppose xn, n running from 1 to infinity is equals to n. So here n running from 1 to infinity, if we put the value of n is equals to 1, then we get 1. If we put the value of n is equals to 2, then we get 2, 1, 2, 3, 4, 5. This is the one example of sequence. Sequence of real number is a function defined on the set of natural numbers whose range set is contained in R. Means this sequence is a function, suppose x, from set of natural numbers to real numbers defined in some definite manner. Here the sequence xn is defined by n running from 1 to infinity n is from the set of natural numbers. If we run n from 1 to infinity, then we get this. So this is the sequence. This is the definition of sequence. Sequence means there is some rule assigned to each and every natural number which gives some real numbers. If we take some another example, suppose if we take this sequence xn, n running from suppose 1 to infinity, as the set is equal, suppose 1 by 2, 1 by 4, 1 by 6, means reciprocal of even numbers. So we can write this xn, n running from 1 to infinity, 1 upon 2n. So this is some another example of sequence. If we run n from 1 to infinity, if we put n is equals to 1, then we get 1 by 2. If we put n is equals to 2, then 1 upon 2 into 2 is 4. Similarly, 1 by 6, 1 by 8 and all other numbers. So this is another sequence. If we we write the third element, third set as suppose the xn running from 1 to infinity, running from 1 to infinity as suppose 1, 1 by 3, suppose 1 by 1, 1 by 3, 1 by 5 and all other numbers. Suppose this is the set of all reciprocal of all odd numbers. So, we can arrange this or write this as function as 1 upon twice n minus 1, 1 upon twice n minus 1. If you put n is equals to 1, 2 minus 1 is 1. So, 1, if you put n is equals to 2, 2 to the 4 minus 1 is 3. So, 1 by 3, 1 by 5 and so on. These are some examples of sequences. Sequence means there is one rule or a function from natural numbers to real numbers, such that if we run n from 1 to infinity, then we get an infinite set. This is the third example. Now, if we get, so suppose this is the fourth one. Fourth example is suppose the set xn running from 1 to infinity, and this set is suppose defined as 2, 2, 2. This is another sequence, and if the one number is repeated in the sequence, then this sequence is called constant sequence. Here the sequence is given by 2, running from 1 to infinity, and this sequence is called constant sequence, running from 1 to infinity. For any value of n, we get the range set as 2. So, this sequence is called constant sequence. This is also sequence, and this sequence is called constant sequence. Similarly, if you write this to 3, 3, 3 and so on, then sequence is constant also, because 3 is the only element in the range set. Now, we will take another example. Suppose sequence is defined by, suppose xn is given by, suppose xn is given in manner, suppose x1 is equals to 2, x2 is equal, and the other element, that is xn plus 1 is equals to xn plus 2. Suppose if you have given x1 is equals to first element of the sequence is equals to 2, and other elements are of the form xn plus 2. So, here x1 is given, x1 is equals to 2, x2, to find x2, 2 means if we put x1 plus 1 is equals to 2, to find the x2, if we can put n is equals to 1, then x1 plus 1, so x2. So, xn is equals to n is equals to 1, if we put n is equals to n here, then we get x1 plus 1 is 2. So, x2 is, we have to put n is equals to 1. So, here x1 plus 2, x1 is equals to 2, 2 plus 2 is 4. Now, to find the third element, here x3, we have to put n is equals to 2, because x2 plus 1 is 3, x3, to get x3 we have to put n is equals to 2. So, x2 plus 2, x2 plus 2, x2 is equals to 4, 4 plus 2 is 6. So, this is another example of sequence. This is xn running from 1 to infinity. This is another example. Now, we will see this sequence, the sequence which is defined by x1 is equals to and all other elements are xn plus 2. This sequence is called recurrence relation or recurrence formula. This is the sequence of REC, recurrence formula. This is the recurrence formula. Now, we will see another example. This is the fifth one. Now, we will see the sixth example of sequence. Suppose we have given that this is the Fibonacci sequence. This is another example, Fibonacci sequence. Fibonacci sequence means the sequence, suppose f, sequence f is given by fn, n running from 1 to infinity, such that f1 is equals to 1, f2 is equals to again 1, and the all other elements are given by fn plus 1 is equals to fn minus 1 plus fn, fn minus 1 plus fn. To find f3, we have to put n is equals to 2, because f2 plus 1 is 3. To find f3, we have to put n is equals to 2. So, n is equals to 2, 2 minus 1 is 1. and this Fn is F2. So F1 plus F2 is F3. So F3 will become our 1 plus 1 is 2. F4 means, so this Fibonacci sequence is given by 1 comma 1. Now the third element is the addition of first two elements. Addition of first two element is 2. Now to get the fourth element we have to add these two numbers. So 2 plus 1 is 3. To get the next number we have to add these two numbers, that is 2 plus 3 plus 2 is 5. To get next number we have to add the last two digits. So here 3 plus 5 is 8. This sequence is called Fibonacci sequence, and Fibonacci sequence is defined or arranged by this rule, that is F1 is equals to 1, F2 is equals to 1, Fn plus 1 is equals to Fn minus 1 plus Fn. So this is the Fibonacci sequence. Now we will see the definition of limit of a sequence. Next topic is limit of a sequence. Limit of a sequence. Suppose let sequence x, this is another notation xn, this is another notation of sequence xn. This notation is same as like this notation xn, en running from 1 to infinity, and these two notations are same. In general we will use this notation. Sequence xn be a sequence of real numbers. Let x is equals to xn be a sequence of real numbers. Be a sequence of real numbers. The real number n, the real number small l is said to be limit of this sequence xn, is said to be limit of sequence xn if for every epsilon greater than 0 there exists a natural number, there exists a natural number, there exists a natural number, suppose capital K, such that mod of xn minus L is less than epsilon, mod of xn minus L is less than epsilon for all n greater than or equals to k, for all n greater than or equals to k. We say that our sequence xn of real numbers has limit L whenever mod xn minus L is less than, for all epsilon positive mod of xn minus L is less than epsilon for all n greater or equal k. That is, this means that a sequence, suppose this is a set in which these elements are the elements of sequence, then we say that the sequence has limit L. This sequence has limit, this sequence means infinite set, these are the elements of the infinite set, and we say that the sequence of real number has limit whenever for every epsilon positive. Here this, suppose this L is said to be limit whenever for every epsilon positive. If we take some epsilon and then this neighborhood, suppose this is the neighborhood of epsilon neighborhood of L, then this epsilon neighborhood of L must contains the elements of sequence which are greater than, where n is greater or equal k. So there must be some k, such that all the elements, so the elements of the sequence are, suppose x1 is first element, x2 is second element, x3, x4 up to suppose this xk, then xk plus 1 plus up to so on. These are infinite number of elements. Then we say that the sequence has limit L whenever the sequence has limit L. Around this L, if we draw the epsilon neighborhood, for every epsilon neighborhood there must be some value of k for which the remaining element, that is xk plus 1, xk plus 2, xk plus 3, all the higher elements of that sequence lies inside this neighborhood. Then we say that the sequence has limit L. For example, if we take the sequence of here, the sequence of real number, suppose this is 0, this is suppose 1, then if we take sequence xn is equals to 1 by n, xn is equals to 1 by n. The elements of 1 by n are, the elements means 1, if you put n is equals to 1, then you get 1, 1 by 2, 1 by 3, 1 by 4 up to 1 upon suppose this 1000, 1 upon 1001 and all other elements. So we can say that this sequence has limit, suppose I will see this sequence has limit 0 whenever, for if we take any epsilon greater than 0 and draw the neighborhood, suppose this is epsilon and therefore this epsilon neighborhood of 0, here I am taking L is equals to 0, then this epsilon neighborhood of L which is equals to 0, epsilon neighborhood of 0 must contains all the elements of xn which are greater than this k, that is xk plus 1, xk plus 2, xk plus 3 must be inside this. Here you can clearly see that this 1 by 2 lies here, then 1 by 3 lies here, 1 by 4 is here, then 1 by 5 is suppose here, and 1 by 6, 1 by 7, 1 upon 1000, 1 upon 10,000, all the elements are very close to 0. So we can for any smallest epsilon we can find the value of suppose k such that the all the remaining elements which are exceeding k by, suppose this is xk, then all the elements for xk plus 1, xk plus 2, xk plus 3 lies very close to 0. So we can say that this sequence has limit L is limit 0. So whenever we can say that sequence has limit, then the all for every epsilon positive there must be some element k of sequence, after that all the elements lies very close to that limit L, then we say that sequence has limit L. We say that the sequence has limit L. Suppose this is sequence, we will take another example. Suppose this is sequence of real numbers and all the elements are here, after this k all the elements lies very close to this point, then we say that this L is limit of this sequence, because after this k all the elements lies this suppose epsilon neighborhood of L, then we say that this sequence has limit L. This is the definition of limit of sequence. And now we will take one note. If the sequence has limit if the sequence has some limit L, then we say that sequence is convergent. We will take one note. If sequence has limit, then we say that the sequence is convergent. The sequence is convergent, and if the sequence does not have any limit, then we say that sequence is divergent. Now we will see some theorems and examples in the next lecture.